again, and in this video we'll be looking at the industrial preparation of ammonia gas. How do we prepare ammonia gas on a large scale? We have discussed in the previous video how we can produce ammonia gas in small scale in the laboratory, but ammonia is so useful that we cannot just produce it in small scale. It is needed to make fertilizer, and these fertilizers are being used for producing food. Hence, we must devise a means of producing ammonia on a large scale. The idea of producing ammonia on a large scale was successfully developed by a man called Fritz Haber. Fritz Haber is a German scientist that looked into the chemistry of ammonia production by using nitrogen and hydrogen as raw material. So you call that process the Haber process, that process for making ammonia industrially. This Haber process involved the use of nitrogen and hydrogen direct combination to make ammonia. The nitrogen that is being used in this place is obtained from air, because air is a very cheap source of raw material, and the hydrogen that is used is obtained from water gas. How then do we utilize this raw material to manufacture ammonia? You make ammonia by reacting 3 parts of hydrogen with 1 part of nitrogen to form ammonia. By passing this mixture over finely divided iron catalyst at the temperature of 450 degrees Celsius and pressure of about 200 atmosphere, then ammonia gas will be produced. To now collect the ammonia is liquefied by cooling. Ammonia is a gas that can easily turn to liquid because it contains intermolecular hydrogen bonding in it. If you observe the nature of the reaction that produces ammonia, you are going to agree with me that it's an equilibrium reaction, which means that it is very difficult for the reaction to go into completion. So what are the conditions that we can use to drive this reaction to favor the formation of ammonia by Chatelier's principle? The reaction is exothermic, which means it does not require so much heat. But if the heat is too less, the reaction will be also slow. So we have to find an intermediate between making the reaction to be fast and not allowing the ammonia to decompose back into nitrogen and hydrogen, because that is the reaction. If our reaction is exothermic and you keep increasing the temperature, you'll be favoring the backward reaction. So you need to decrease temperature to favor forward reaction, and you must be very careful in the way you decrease temperature to ensure that the reaction did not go at a very slow pace. You know, we are doing industrial manufacturing, and in this case you need to produce ammonia in a large scale over a short period of time. So you need a reaction that can make it to be very fast and also to not go back into this backward reaction. So what are the conditions that will favor the formation of ammonia in the Haber process? Number 1, we decrease temperature. This is why we use temperature of just 450 degrees Celsius. And to compensate for the loss in the rate of reaction, that's why we have to use catalyst. So it's a catalytic reaction. We use catalyst of finely divided iron to drive the reaction to become fast. So at lower temperature like that, we can be sure that the reaction will be going forward instead of going backward. Then we also increase the pressure, because the forward reaction occurs with a decrease in number of mole. It occurs with a decrease in volume. So when you increase the pressure, you know what will happen. The equilibrium position will shift to the side that the number of mole is lower. And if you look at it very well, you will see that at the right hand side we have 4 mole of the gases. That's talking about nitrogen 1 mole and hydrogen 3 mole, making 4 moles, right? Now at the product side we have 2 moles of ammonia. So which means the product side have lower mole than the reactant side with 4 mole. So to drive it forward, you are going to increase the pressure. When you increase the pressure, the gun will shift to the side that has lower number of mole of gases. So that's why increase in pressure is one of the factors that we use to drive the reaction forward. And we use a pressure of 200 atmosphere, 200 atmosphere of pressure. Then finally, you can liquefy the ammonia. When you remove the ammonia, by liquefying it as it is being formed, there will not be ammonia to decompose back into nitrogen and hydrogen. So you can be sure that most of the products formed will be ammonia. So these are the conditions that we use to favor the formation of ammonia by the low Chatelain's principle. So what are the physical properties of ammonia? We want to look at the properties of ammonia now. The physical properties of ammonia. Ammonia is a colorless gas with choking smell. The smell is choking and the gas is colorless. Number two, it's highly soluble in water. Because of that, you can use it to demonstrate the fountain experiment. The fountain experiment to demonstrate gases that are highly soluble, not just soluble, highly soluble, greatly, extremely soluble in water. So ammonia is another gas that is extremely soluble in water after HCl. And ammonia is also poisonous in large quantity. It's poisonous. Ammonia is less dense than air, and the reason we collected it over by upward delivery in the previous video. And also you cannot collect it over water because it's soluble in water, so you don't want your gas to get lost inside water. Then it turns red litmus paper blue. In fact, virtually the only gas that can have such effects on litmus paper, turning it from red to blue. And that's one of the indications that a gas is ammonia. If you put a moist litmus paper and it turns from red to blue, it's most probably the gas is ammonia gas. So let us peep into the chemical properties of ammonia here in this place. Number one, ammonia burns in oxygen with a yellow-green flame. Take note of the flame color of ammonia. And when it burns with oxygen like that, it produces steam and nitrogen. However, the product that ammonia forms when it reacts with oxygen depends on whether you use a catalyst or not. If you don't use catalyst, your product will be nitrogen and steam. But if a catalyst is used in the combustion of ammonia, the product will be not just nitrogen and steam alone. The product will be nitrogen 2 oxide, that colorless gas with steam. That will be the product. And the normal catalyst, the normal thing that we use as the normal element that we normally apply as catalyst is platinum rhodium catalyst. So normally used as catalyst for that reaction. Then that NO that was formed by the catalytic reaction of ammonia with oxygen can easily oxidize to NO2. I've been telling you that it has strong affinity for oxygen, so it can easily oxidize to NO2 to form that reddish brown gas. That's the color of NO2. NO itself is a colorless gas, but NO2 is reddish brown in color. That reddish brown gas can later react with excess ammonia to form a white film of ammonium trioxonitrate 5, as you can see on the screen. Okay, ammonia can also react with HCl gas. In fact, this is a very common reaction of ammonia and very easy, very popular reaction of ammonia. When it does that, there's a formation of a dense white film of ammonium chloride. As you can see on the screen, you form dense white film of ammonium chloride when ammonia reacts with HCl gas. So we are seeing a case of two colorless gases reacting to form a white solid. God is powerful. Alright, let's see some other reaction of ammonia. It can also react with copper 2 oxide. Copper 2 oxide is a black solid. When ammonia reacts with it, you can see this uh, this reaction flags now is meant for the production of ammonia. You can see that ammonium chloride and slake lime, those two combination are meant for producing ammonia gas. So when the ammonia gas is produced, it becomes dried here using quicklime. That's a U-tube that you pack quicklime inside it. So that ammonia gas will enter into the copper 2 oxide chamber. You call that a combustion tube where the copper 2 oxide is being stored. So as the ammonia is entering inside, it will be turning into nitrogen gas. And that black copper 2 oxide will be changing into brown metallic copper. So the gas will pass through anhydrous copper sulfate. The gas will pass through white anhydrous copper sulfate to absorb the water, because don't forget that water vapor is produced alongside nitrogen. So that white anhydrous copper 2 sulfate help us to trap the water, so the compound will turn to blue, because it is normally used to test for water. It turns from white to blue if water is introduced into it. So nitrogen will just pass through undeterred and be collected over water. So this is how ammonia gas reacts with copper 2 oxide. So this reaction shows that ammonia gas is a reducing agent. It reduces copper 2 oxide into ordinary nitrogen gas. Ammonia is also used in laboratory to test for metallic ions. There are two alkali that normally use sodium hydroxide followed by aqueous ammonia. In drops and excess, you get different colors that indicate the presence of a particular cation or absence of such cation. You can also react ammonia with carbon 4 oxide, and here it gives you urea. The reaction occur at 150 degrees Celsius and 150 atmosphere to produce urea. Urea is very important in chemistry because it is used by farmers as fertilizer in their farm. Also with limited chlorine, ammonia can react with chlorine to form hydrogen chloride and nitrogen. However, because the ammonia is in excess, that HCl that was formed in gaseous state, not in solid state, in gaseous state, can react with more ammonia to give us white fumes of ammonium chloride. That is with limited chlorine. What happens if ammonia reacts with excess chlorine? Another product will be formed, an explosive oily liquid called nitrogen 3 chloride will be formed when chlorine reacts with ammonia, and the chlorine is now in excess. So you form a colorless liquid called nitrogen 3 chloride, and HCl gas is produced, as you can see in that reaction diagram there. God bless you. Amen.